Okay, let's talk about our first equation of state, and that's the perfect gas law. In fluids, an equation of state is basically an equation that you can use to find properties of the material in question. So let's take a look at the density of liquids. So we have the density of liquids. So what do we know? Well, liquids are generally difficult to compress. And because they're difficult to compress, their density pretty much stays constant. We can assume that they are incompressible. So density itself is really just strongly influenced by temperature. So density is a function of temperature only. And so because of this, densities are usually available on a table that is correlated against temperature. So on the other hand, let's look at gases. Still a fluid, just a different kind of fluid. So gases are generally easy to compress. And since they're easy to compress, that will change their density. And so that means so the density of a gas is still a function of, I'm sorry about that. Let's go back a line. It's still a function of temperature, but it will also be a function of pressure. Because now we have both those things going on. And so it would be very difficult to correlate that via tables, because you would need a bunch of tables at a certain temperature and then all these different pressures. So the way that we relate the density of gases is through equations of state, and those equations of state really depend on the type and molecule shape of the gas. Now, for us common monoatomic and diatomic gases, those would be, monoatomic would be something like helium, which has a completely filled electron shell, so it doesn't bond with anything. A diatomic would be something like hydrogen, where you need two hydrogens to stabilize that outside shell. Oxygen is another one. So we have a ton of them. And a lot of gas mixtures, most importantly air, can be modeled by what we call the perfect gas law. So the perfect gas law is fairly simple, and it really is just the pressure of the gas is going to be equal to the density times a gas constant. Now this R is to the gas constant for that particular gas times the temperature. Okay, so I changed slides on here to start with the clean one. So pressure is equal to R times T. Now, the first thing is that R, so we have to look it up for different gases. Probably the most important one for us is going to be the R of air. And so air is 287 joules per kilogram times the Kelvin. And it's also 1716 foot-pound force per slug times degree ranking. And so foot-pounds is a unit of energy, just like joules. What is a joule? Just remember, a joule is a Newton times a meter. But these are the typical values for it. Now, all other values for other gases will be tabulated. You can look them up. But as you look at it, the important thing to note is Kelvin, degree ranking. So that tells us something about our equation. Temperature has to be absolute temperature. If you do not use the absolute temperature, the units aren't going to cancel out right, and you're going to get the incorrect answer. So one other thing to keep in mind is pressure is also absolute. So if you have a gauge pressure, you do have to convert that over to a absolute pressure, that pressure coming from zero. And that is the perfect gas law, and it will be used quite a bit in this class.